Section 2.2, these are basic differentiation rules. Okay, so you will need to memorize these, and so as you work with them, you're going to memorize them automatically, especially this particular section, because these are very basic rules. And we're going to talk a little bit about why the rules actually make sense, why they work. But the first thing I'd like for us to do is to actually just get them all written down. There's 6 of them we're going to take a look at. So here are the first 3. Basic derivatives. The constant rule says that if you have a constant, there it went. If you have a constant, f of x equals c, so c is a number, and you take its derivative, it's 0. Okay? The reason that's true is because if you have a constant, it means it's a horizontal line. What's the slope of a horizontal line? 0. 0. That's why that's happening. Okay? The second one, a power rule. And there's sometimes one, your book doesn't do it, but there's sometimes one that happens in between these. So let me tell you the power rule, and then I'll do the in-between rule so you can see it in case you're familiar with seeing it before. Power rule says that if you have x to the power n, then the derivative of this is n times x to the n minus 1. I think that might be the only thing my husband remembers from calculus. This one rule, one thing from that many years ago. That's how frequently you use it. It's very, very common. Okay? So if you have any power, and n can be anything. It can be a whole number, like 5. That's fine. So you bring the 5 down, and the new exponent is 4. It could be a fraction. So if you're not good at subtracting fractions, you might want to brush up on that just a little bit. It could be a decimal. It could even be a radical. Okay? It could be any number you'd like. And this rule will hold. And then constant multiplier rule says that if I have a number here, like this, in front, then I can kind of ignore it, and I can just take the derivative of whatever else I have in the problem and multiply it by that constant when I'm done. So I have c, and then I have g prime of x. Okay, so here's your sort of freebie. This is the one that some books put in it, but yours doesn't. Some books put in an actual one for a line. So if you had, say, y equal mx plus b, it's really a combination of a couple of rules. So here's y prime. So this m is this constant multiplier like the c here. So the m just is going to be part of the problem. Okay? X is like having x to the 1. If you had x to the 1, this rule says I'd bring the 1 down in front, and then I'd have x to the 0. Do you remember what x to the 0 is? 1, right? So it would, the derivative of x is just 1, is what that means. And then the plus b is a constant rule at the end, right? And its derivative is 0. So we can kind of work through that like that, sort of like piece by piece. But here's what else you can do. Y equal mx plus b is a what kind of an equation? Linear. A linear equation. And derivatives are supposed to be just the slope of the equation. What's the slope of y equal mx plus b? It's m. Wow. It's m. That's it. That's why that works. So there's really nothing mysterious about it. If you forget or you're not thinking about it, sort of fluidly, and you want to go through it piece by piece, you're still going to get m. But it really is that simple. Derivatives are slopes. The slope of a line is just m. Okay? All right, there are 3 more. Do I have them written separately? No, I do. Yeah, they're fine. Okay. First one is sum and difference rules. So if you have 2 pieces added together, much like I just had on my freebie here at the end, I had the mx thing added to the b. What you saw me do is actually appropriate. You can take the derivative of each piece individually and multiply them. Didn't mean multiply them. Add or subtract them. That's what I meant to say. So the g prime of x here, the h prime of x here, and then whatever sign was between them stays between them. If it was addition, it's addition. If it was subtraction, it's subtraction. And then sine and cosine. Got to get some trig in there somewhere, right? So this is a fun one. Derivative of sine is cosine. And the derivative of cosine is actually negative sine. And in terms of trig rules, these are the 2 that we use most frequently, number 1. And they're the easiest ones to remember. We are going to do secant and cosecant and tangent and cotangent. We're going to do all of those later, but they're not quite so straightforward and clean. All right, so these are the two trig rules that are our basic differentiation rules. And we definitely need some examples. So that's what we're going to do next. Okay, so we've got y equals x to the 7th. The directions say to use the rules of differentiation to find the derivative of the function. So what I'm actually doing in this problem is I'm shortcutting that limit definition from before. Okay? If I were to do the limit definition on this problem, the next thing I would have to do is I would have to write down limit as h goes to 0, and then I would have y plus h, or not y, sorry, x plus h to the 7th minus x to the 7th all over h. And I don't want to FOIL something out 7 times. Yeah. So we're not going to do that out 7 times. 3 times maybe. 2 times for sure, no problem, but not 7. Okay? However, we have these simple, basic derivative rules now that say that we actually can shortcut that system because basically somebody else found out that this rule works with that limit definition all the time, and now we get the benefit of their work. That's what it is. Okay? So what's the derivative of x to the 7th? Well, this is that second rule right there, power rule. What do I do with the 7? I bring it down to the front. I write my variable, and then I decrease my exponent by 1 to make it a 6. And that's it. Who's a fan? Yeah? Okay, lots of hands raised. That's great. All right, now this next one always throws people because of the pi. Pi is not really meant to throw people, but when you see the letter pi, you think of it as exactly like what I just said, that it's some sort of a letter, right? Like an x. But it really isn't, right? It's a letter that represents a numerical value, correct? So when you see pi, you need to remember pi is just a number. And because it's just a number, it's acting like a constant multiplier in this problem. All I do with it is simply write it down, and I look at what's coming after it, and I deal with that one as its derivative. Okay? So I've got f prime of t. Pi, I said, like, is just a number. And then what's the derivative of cosine?
Negative sign.
Okay. Now, because it's negative sign, I don't want to write down minus sign because then it looks like I'm taking pi and subtracting it. So put it before the pi. Yeah. Just like that. Okay, put the negative in front of the pi to avoid any kind of confusion of addition or subtraction. That's it. All right. Okay, now not all of them are quite so clean and look exactly like one of the rules, but often we can actually do some sort of a revision of rewriting something to make them look like one of those rules. So here's an example of that. I have a 4, I've got a 3, I've got an x squared, but it looks like there's something in a denominator, and if you'll take a look back at those rules, they didn't say anything about what to do when I had a denominator, right? And we will encounter what to do when we legitimately have a denominator that we can't deal with later on. But we can deal with this one, all right? So how do we deal with this one? Well, first of all, understand that the 4 and the 3 don't need to move because they're just numbers. It's just 4/3, okay? So don't go trying to move the 3. The 3 is just fine where it is. However, the x is not. So instead of the x being x squared in the denominator, what I'd like to do is I'd like to pull it up to the numerator. And if I do that, what would its new exponent be? Negative 2. It's property of exponents, right? And then I actually have something that looks like the rules that I had before. So I can differentiate this next. So to differentiate this, the 4/3 is a constant multiplier, so I simply write it down. And then I need the derivative of the x to the negative 2. So that's power rule, right? And I told you those power rules work with any exponents, and I didn't actually mention negatives, but it's true. They work for negatives just fine as well. So what will I do with the negative 2? Bring it down. And then I'll rewrite my x, and then I need to decrease the exponent by 1. Negative 3. Yeah, it always catches people too. Don't feel bad. All right, so we need to decrease it by 1. It's actually going to take negative 2 minus 1 is negative 3. Everybody good with that? Okay. Now, this is a mess. You guys agree with me?
Yes.
Now, here's a cool fact. Right here is where you get to leave it on one thing that you do for me. Okay, so somewhere in your syllabus it talked about something called a gateway or a basic skills test, exam, quiz. I don't know what I called it, but I used either the words gateway or basic skills. Once we finish with all the derivative rules, so it's like next week, or it can't be even next week, probably the week after, we will have a 50 point, so it's like worth half as much as an exam, test quizzy thing. And you can stop right here.
What?
You don't have to simplify it on that one. Okay? We don't allow a calculator. That is one reason why. It's not really the reason why. The real reason why is because my goal in that particular assessment is to test to make sure that you can do derivatives. That's it. Because after this, we are going to do it on this problem after this. The simplification is not calculus. It's algebra. Okay? So that particular quiz allows me to isolate some of the actual calculus concepts that we're working on, aside from the algebra stuff that we always are intermixing it with.
So if I show all the works and simplify it, would you count me off?
On the quiz?
On the quiz.
No, but if you make a mistake in your simplifying, yes.
Okay.
Okay? Yeah, you can simplify it, but please understand, if you do and you miss it, it's going to be highly unfortunate. Because on that quiz, if you make a mistake, you miss the question. There's no partial credit. And we'll talk more about it later because you can repeat the test multiple times of different versions of the test. That's why. But this is one of those rare opportunities. I know you had this sort of massive rare opportunity that said, oh my word, if I take this first review and I spend, how many hours did you guys spend working on your review on WebAssign? At least 3, I think, probably, if you finished it really.
Mm-hmm.
Yeah?
2, maybe 1.
2? Okay. That's a lot of work. Okay, are you guys with me? It's a lot of work for 5 points. Would you agree? Your basic skills quiz, gateway, whatever, you have an opportunity for 5 points of bonus. And you have the opportunity in the same amount of time as you have the opportunity to not get it too. Okay? So if you want to, I'll let you go back and review on how you get those bonus points for that skills quiz later. But this is where you would stop. Now, we're not going to stop here for WebAssign. We're not going to stop here for our homework. We're not going to stop here for our tests. It's just on that one assignment that we will. So we're going to clean this up. Now, a couple of rules of thumb. If the question started out with positive exponents, and it did, x was squared, then the question needs to end with positive exponents. Okay? If it started out with negative exponents, it'd be fine for it to end in negative exponents. If it starts out with radicals, you're going to end with radicals. Okay? So however the question starts is how the question's final answer should look at the end. Okay, so as we're taking a look at this, we've got a few pieces of information. These two constants here at the beginning, the 4/3 and the -2, those can be combined. What would those give me? Negative 8/3. And then I've got x to the -3, but I don't want negative exponents. So where will I put that? Back on the bottom with the 3, and I'll make it x cubed. This is how the final version of this should look. Okay, Dawson.
Yes, put the prime. Yeah, prime.
Thank you. I left it off. Was that your question too, Rini?
Yes.
Yes, thank you very much. I do need that. Okay, any questions on that one? Okay. Now about this one.
Yeah, lots of questions.
This one really actually looks like I cannot use at all what I normally would have used. But I can. Fallon, do you have an idea about what you could do?
Oh, yeah, well, what I was going to say we haven't done yet.
Okay,
So
the
both.
quotient rule, but
Yeah.
there's something easier I can actually do in this problem. It's way easier than the quotient rule.
Can you just take the derivative of each piece?
You cannot take the derivative of each piece. That is definitely not okay.
You cannot. You could factor. What happened to 4?
Do you have an idea, Addison? It's okay to say no. I just see your brain like moving back here.
Change the x on the x2 on the bottom to x to -2.
You could, but that's still just going to leave it as a product. And I don't have any rule for the products yet. Mooney?
Can we break out each of them?
Yes. Okay. So
Oh, I see.
we're going to break this apart into 3 fractions.
Okay. Oh, okay.
Okay, we can do this because the addition and subtraction is in the numerator as opposed to being in the denominator. If it were the denominator, we couldn't do this. But because it's in the numerator, we can. Okay? Now, usually when you work with fractions, you start with something that looks all broken apart and you sort of get common denominators and you mush it back together, right? We use the operations of fractions in the other order. but they work in this order as well. So some of these simplify quite nicely. The first one, x cubed divided by x squared, what is that? X. What is 3x squared divided by x squared? Negative 3. The part at the end, though, looks an awful lot like the last problem I did, right? So I do not get to simplify them when I actually have to rewrite it. How will this one get rewritten?
The 4x to the negative 2.
Right, 4x to the negative 2. So far, there's no calculus that has been used. That was just an algebra simplification step to allow us to use the calculus, which we will now use. G prime of x. Now, we're going to take these a piece at a time. This is that sum difference rule that allows me to do that. I can do one piece at a time. So what's the derivative of x?
1.
It's 1. Because remember, x is a linear equation and its slope is 1.
Oh.
Or if you want to think about it as being x to the 1 and pull the 1 down and decrease it, you'll get 1 as well. Okay, what's the derivative of the negative 3? 0. And I don't need to write it, but I will just so that I can remind you that we took it. It didn't just sort of disappear. And then this piece right here, that's the power rule, right? So technically, I could write down the 4 if I want to, and then I could deal with the x to the negative 2. But the more you do these, the more comfortable you're going to get at it, and you're just going to take the negative 2 and multiply it in one step, probably. So what's negative 2 times the 4? That's negative 8. X to the negative 3rd. And if this were the gateway, you'd stop right here. Okay? But it isn't. So you're not going to stop right here. You're going to take one more step. You're going to get a 1 at the beginning. I don't need to write down the minus 0, right? But I do need to change the negative 8x to the negative 3rd. Negative 8 over x cubed. And this is a perfectly reasonable way to leave it written. You might actually see common denominators employed at some point on this, and they might write this as x cubed minus 8 over x cubed. There's no reason for you to do that. I just want you to know that if you were to see this sort of on somebody else's work, or if WebAssign showed you this is your answer, you might be like, oh my goodness, how did they get that all in one fraction? This is what they did. They just got common denominators, okay?
Oh, okay.
They're just multiplying this 1 by x cubed over x cubed. Okay. So there's nothing sort of special about it. I just don't want it to surprise you if it happens. Okay, any questions on that one? Because the next one's got radicals. Oh, yeah.
Which radicals are just...
They are. Radicals are just exponents. So I think the first thing I should probably do is to rewrite it that way. So what would it look like instead of cube root of x?
3, 1, 1/3.
X to the 1/3. And what would it look like instead of the 5th root of x? X to the 1/5. Okay? Now, in spite of the fact that maybe you don't like fractions near as much as whole numbers, it looks like the forms of things we can deal with, right? Okay. So let's deal with it from that perspective then. What is the derivative of x to the 1/3?
Negative 2/3.
Okay, negative 2/3. So I need to take that new exponent, or the way I get the new exponent is by taking the 1/3 and subtracting 1. So 1/3 minus 1 is negative 2/3. Negative 2/3. We're going to do the same thing with the 1/5. I've got my 1/5 I pull down. And then I need to take the 1/5 minus 1. Negative 4/5.
Yeah.
Okay? If we were on the gateway, we'd stop. Okay? But we're not. The problem started out with radicals. So the problem needs to end with radicals as well. Okay? So we're going to change this back into what it should look like. So the 1 stays on top, the 3 stays on bottom. Negative moves it to the denominator. Okay? 2/3. Well, the thirds part of it makes it a radical. That's the 3rd root. And then the 2 stays with the x. That's how you rewrite a 2/3 power. This is x to the 2 over 3. It is so much uglier. I agree. I totally agree.
Do we have to write it in the radical rather than just like x to the 2/3?
Yes, because the problem began that way. WebAssign might allow you to not do it, but when I look for it on a test or something, I will look for it to be in the same form that it started with.
So if it's not,
So-
if we started with a fraction, do you want us to leave it fraction?
Yes, if it had started with a fractional exponent like the 1/3, like if we actually started at this x to the 1/3 plus x to the 1/5, we would stop the problem there. Okay, we have one more little piece, and then I need to let you go. So this is a 1/5, so we've got 1 over the 5. How will I rewrite x to the negative 4/5? It's in the denominator, that takes care of the negative. 5th root of x to the 4th. Fantastic. And then we're done.